Alright, let's practice setting up another physics equation here. This is number 21 from page 61 of your textbook. The car is traveling 20 meters per second when the driver sees a child standing in the road. Alright, I have to apologize for my drawing here, but here we have a car. And I'm going to put some wheels on the car. It's driving down the road and it sees a child standing in the road with a probably not the happiest moment. There's a car heading right at this child. He takes 0.8 seconds to react, then steps on the brake. So this is the driver that takes this much time to react. Slows at 7 meters per second squared. How far does the car go before it stops? Okay. So we don't know the distance. We don't know the distance from the car. We'll just mark a midpoint here. We don't know this distance here from the car to the child. But it does give us a few details. The car is traveling initially at 20 meters per second. So I'll just put a velocity arrow here. It's going 20 meters per second. And it takes the driver 0.8 seconds to react. So it travels a certain distance at that velocity before it reacts. So let's say that the time to get from this position to this position, we'll say this is 0.8 seconds from where the car is to the moment the brakes are here. So I'll write here, hits the brakes. Right, up to that point, the car is going 20 meters per second. That was its velocity. And we'll assume the velocity was not changing. The car was cruising at that point. So that means that the acceleration up until that point, when the velocity is not changing, that equals 0. The car is going at a steady pace. But now, from this point on, the velocity is going to change. The velocity, which starts off big, is going to decrease and get smaller and smaller and smaller as the car slows down. So the velocity is decreasing, which is lucky for the child. The acceleration is going to decrease. Okay, so the velocity is decreasing. The acceleration will actually be in the opposite direction. Acceleration is, it doesn't say it's changing, so I'll just draw 3 arrows roughly the same length here. It says that the acceleration is now 7 meters per second. Because the acceleration, per second squared, sorry, 7 meters per second squared. Because the acceleration is acting in an opposite direction to the direction of the car and slowing it down, it wants to know how far does the car go before it stops. This is actually a kind of a tricky question because you will have to figure out the distance from this position here, before the car hit the brakes, to the point when the car hits the brakes. We don't know. This will be kind of the first distance. Then we'll need to calculate. Once it hits the brakes, acceleration changes. It becomes 7 meters per second in the opposite direction. So I wrote a negative sign there because it's negative. So we're going to have another distance, and we'll assume that it stops before it hits the child here, hopefully. But we have 2 separate sort of calculations to do. One when the car is traveling 20 meters per second with an acceleration that is not changing, and the other when we don't know what's happening. We know the velocity is decreasing. We know that the acceleration is constant in the opposite direction. These are the clues that we are given. So in the first example here, if I just extend this page a little bit, Okay. To calculate kind of part one, where the car is traveling at 20 meters per second, I would set this up like this. I would say that the velocity, the initial velocity, is 20 meters per second. Okay. The acceleration is 0, or it's constant. We do not know the distance that the car travels, but we do know the time. We know the time equals 0.8 seconds. So knowing that, it would be good to find the distance the car travels before the car hits the brakes. So that's the first calculation, and if we were to solve, we're not going to solve it, but we're just trying to set it up. If I go back and look at my equations here, we would use the same as the first equation. We have a velocity, 20 meters per second. We don't know the distance, but we know the time is 0.8 seconds, so we can put those numbers into this equation and calculate it. Okay, we'll go back to our assignment here. The next step here, we know a couple things. One, we know the initial velocity was 20 meters per second, just at the moment the brakes were applied. And we know that the final velocity, that's not a very good F, is 0 meters per second. That car is going to stop. We know the acceleration, it's in the opposite direction to motion, so it's 7 meters per second squared. We don't know the time it takes to do that. And we don't know how far the car goes either. But that's what this question is asking for ultimately, is what is the total distance traveled? Okay, so we do know a few things. We know an initial velocity, a final velocity, and an acceleration. Let's go back to our sheets here. Okay, so if we know acceleration and we know velocity, an initial and final velocity, we can use this equation. I mean, there are many equations that we could possibly use, but this one here will help us calculate. Sorry, I don't know what that's doing, but it's helping, well, the screen is doing some crazy stuff here. Bear with me for a second. It automatically saved that, but basically there was a formula there for using, let's open it back up. I apologize. It's still circled in green, which is good. We could plug in this is our final velocity. Here's our initial velocity. We know our acceleration is negative 7 meters per second squared. And we don't know what our distance is, but that's what we're trying to calculate here. So this is one possible way of solving the second part. Once we find the first distance and the second distance, we would just simply add them together to come up with an answer to the question, which is how far does the car go before it stops? Okay. It's a more complex one for sure. Let's do one more, and I'm going to do question 24 from the same page. And these are not part of the assignment, but they're just good practice, so to give you an idea of how I solve these types of problems. Stay tuned.